Recording doesn't sound too awful. But then we take a look at, say, just one of those amino acids, clean up the structure a little bit, make sure we don't have all those pretty pictures on it, get rid of all the colors, and just show the kind of the basic structure on it. It's kind of a leading question. Is there an issue when you look at this amino acid? Okay, and you're like, yeah, it's not a big deal. I don't need to worry about that. What was your least favorite chapter in organic chemistry? What was it looking at? Enantiomers. Okay. There's one vote. Anybody else want to challenge that? Say, nah, I didn't like this part, of course. Everybody didn't like enantiomers. Okay. Enantiomers, mirror images, that kind of fun stuff. Why would you have mirror images? Because you had a chiral center. How do you know you have a chiral center? Carbon attached to 4 different things. Or really distinguishable things. Son of a... Okay, well that set's wrong. So, you take a close look at that amino acid structure. What do you see? There's a chiral center. What does that mean? Think about our amino acids. How do they do that? It could have an enantiomer. Okay, well, which one's the important one? How do we figure out which one was the important one when we looked at, I think ibuprofen? Could be wrong on that. I know it's a bit of a stretch. Probably don't have the structure of ibuprofen memorized. Yeah, I really did have to do that. Ibuprofen is a chiral molecule as well, I believe, or naproxen, one of the two. What's the issue?
One molecule is beneficial, the other molecule is poisonous.
One molecule is beneficial, the other one's poisonous. Uh-oh. Our whole basis for proteins has a building block. It has potential for one molecule being beneficial and one molecule being poisonous. That's potentially an issue. Okay. So how does biology get around this? It's really quite simple. Make sure that whenever we use those amino acids, which amino acid do we use? The right one. Whichever one the correct one is, and we ignore the other one. What? So for those of you wondering, I was freaking out over L. There it is. In the little stack somewhere. So, we do have a problem here. That central carbon, the one with the R group, is a chiral atom. Okay, so one thing that we can throw in there just to be confusing, or not confusing, but kind of clarify, we said our chiral atom needed to have 4 different, different groups attached to it, right? How many groups do you see attached to that? 3. Why is there a 4th? There's an implied hydrogen that's hiding back there. Okay, that's our 4th group, right? So we do have those 4 different groups. And so this is one of the reasons potentially why I didn't like biochem, is that you then have to remember which form was the correct form. Is it the one where the hydrogen is wedged and the R group is dashed? Or is it the other one? Because it kind of makes a difference. In one case, it's actually useful. In the other case, biology doesn't even recognize it. Okay? So that's kind of an important thing to note and theoretically remember. I don't know about you all, but my memory is awful, and I can never remember which one. Okay? So hopefully, in these slides, we'll achieve what that answer was. Unless somebody wants to jump out. Anybody remember what it was? You all taken like lots of bio classes, haven't you? They didn't tell you like, oh, it's this amino acid. No? What's that? What type of amino acid? Which chiral molecule is the important one? Where are these letters coming from? Ooh, L configuration. There's an interesting question. What do you mean L?
If you do the priority functional groups, it rotate counterclockwise.
Is it levo and dextro?
So there's levo, there's dextro, there's doing priorities according to which nobody ever remembers. In fact, I really forgot what it was. The Kahn-Ingold pre-log rules, okay? And saying how do our priorities kind of project around kind of a steering wheel, okay? To generate R and S. So we have R, S, we have levo and dextro, which gets translated into lowercase l and lowercase d. Then we get plus and minus coming from how the molecule rotates light. Okay. So how the molecule rotates light is an experimental observation. Like you'd think that one's pretty useful. Unfortunately, it doesn't necessarily match the structure. So that's why we invented R and S. Okay? Because when we look at the structure, we don't have the experimental data, so we just kind of make things up. So then what's with the levo and dextro? Well, the levo and dextro were ultimately a different way of saying plus and minus, because when we looked at how light rotates off of a zero line, we decided that positive and negative was too ambiguous. So instead of just teaching everybody positive and negative, like to the left is negative and to the right is positive, we said we also have to remember levo and dextro. Okay, and that's where we got the lowercase l and lowercase d. And unfortunately, when Ray here mentioned L amino acids, what is that L? Can you visualize it, Ray, in your head when you're thinking L? Can you describe to me that L? I am kind of trying to delay time. Is it a lowercase l? No, it's an uppercase L. Well, that's because it came first in our sequence, right? No. Actually, it's a capital L because it's not lowercase l, it's not lowercase d, it's not r, it's not s, it's not positive, it's not minus. It's an entirely new system for labeling chiral molecules. Because we didn't have enough confusing within that section on its own that biochemistry decided to develop its own labeling system to identify chiral molecules. Which is awesome for you because you now have yet another thing that you get to memorize. Okay? Lucky you. Turns out it's not horrible though. Okay? So one of the things that biochemists go through and do is they don't like dealing with wedges and dashes. Okay? So what they'll do is change the viewpoint on the structure. So when we're looking at that middle structure, all of those solid lines mean they're in the plane of the paper. Okay? We clearly have a problem that R can't be in the plane of the paper. It's either wedged or dashed. Okay? But that's kind of our focus. So chemists come along and say, well, I want to change my view on that molecule. And we change that view, we end up with Newman projections, okay? Hayworth projections, different ways that we can represent that structure. One of the representations that come out of it happens to be known as Fischer. So Fischer went through and looked at that molecule and said, well, I'm going to change my viewpoint on the molecule so that it matches these rules. And when it matches these rules, I'm then going to arbitrarily say that life becomes easier because I followed all these rules. Biochemists get away with saying Fischer's the greatest thing ever because they don't follow any of the rules, they just draw the Fischer. So they skipped all the rules and just jumped to the end and then say, of course it's easier. Well, of course it's easier because you've ignored the science behind why we're looking at it that way. Okay, so how do we convert that structure into these Fischer projections? So what we've got down below are the Fischer projections. Notice there's wedges and dashes. And we said the whole reason biochemists liked Fischer is that there's no wedges and dashes, and yet we have wedges and dashes. Okay, so what's happening? Well, Fischer takes the carbon chain and organizes it on the vertical axis. Not only does he organize it on the vertical axis, he puts the highest priority carbon of that chain at the top. Okay? This goes back to those Kahn-Ingold pre-log rules, which nobody remembers the name of. A carboxylic acid is higher in priority than a carbon. Okay? So it's, by definition, going to be at the top. Okay? When we go through and organize it that way, those atoms have the potential of either being aimed at you or away from you. Attempt that real quickly with one. So there's our carbon chain. Ignore the atoms, or the red and the blue. There's our carbon chain. So what he's saying is that we're going to now take this so the carbon chain is up and down. Okay, I could have done that. Okay, or that. Or that. Or that. Right? 4 different ways we could have viewed it with that carbon chain vertical. Okay? He said that the sideways ones we don't want, we actually want it spun. So literally the carbon atoms are stacked on top of each other. And that's what we're attempting to show here. Okay? So it can either be organized in this fashion, okay, where the middle carbon there is the one coming at you and the other 2 carbons are going where? Away. Or it could have been that, in which case these top 2 carbons are coming at you. Right, so we'd have wedges versus dashes. Fischer went through and said, you know what, I'm only going to look at it where the carbon chain, so I'll pick a center carbon, the carbon chain will always be aimed away from me. So if that's the carbon I'm looking at, the carbon chain must be dashed going away. Or what if I shifted my view to this carbon? Well, then this carbon, as part of the chain, must be organized so that it's away. Why does this become a bit weird? If we look at the molecule, what do you have to constantly do? You have to constantly spiral it to get it into that viewpoint. But once you've done that, you can then kind of imagine you get this straight line. Right? Where the carbon chain is always aimed away. Well, if the carbon chain is always aimed away from you, what about the 2 other groups? They will always, by definition, be aimed at you. There is no choice. That's the only option. Right? So if we force everything into this orientation, what does that then do for us? Well, if I'm in a Fischer projection, that means everything on that vertical axis must be away. So it's by definition dashed. Well, if I know by definition it's dashed, what can I then do? How did I know that was a chiral atom? 4 different things. Do we see 4 different things? No. You said there was an implied hydrogen. How do you know there's an implied hydrogen? Carbon has 4 bonds. So as soon as we know what carbon has to have, by its definition, we can then start to imply useless information, like hydrogens. Now that we know we're in the Fischer projection, and we by definition must have that carbon axis all aimed away from us, what can I now imply? The directionality of those bonds. I don't need to specify dashes anymore. I can change those into solid lines. And so, let's see. I don't think I did. So instead of drawing those out as wedges and dashes, I can then draw that structure, COOH, H, and H2R. Right? And we end up with the classic kind of cross notation of Fischer projections. You'll sometimes hear them referred to as bow tie notations. The bow tie in a traditional Fischer projection doesn't show up because the bow tie is referring to those. You got a little bow tie hanging off right there. But those are wedges. That's how we know it's a bow tie. When we look at the Fischer projection, do we need to specify the directionality? No, because it is implied within the structure itself. Okay? So we're kind of scaling from one potential view, organic chemistry, into a slightly different view, and then saying, because I'm now forced into this view, I can now change some definitions, and I don't have to worry about wedges and dashes because they become implied into my structure. Kind of makes sense? With one chiral atom, not a big deal. Okay? Why would we choose one over the other? really there is no difference. Okay? And that's typically why in organic chemistry you don't see a lot of Fischer projections, because we're looking largely at one chiral atom. But as we continue to propagate through biochemistry, we'll run into carbohydrates. Carbohydrates have upwards of 4, 5, 6 chiral atoms. When we start scaling in that many chiral atoms, it becomes very confusing to deal with the line angle wedges and dashes, and so they always get converted into Fischer projections. And so we'll see Fischer projections again, probably where it's a little bit more relevant. Okay. Now back to Ray's comment on the L. Notice here it says capital L. So there's R, S, plus, minus, lowercase d, lowercase l. Capital L looks at the chiral atom in our amino acid. Okay? And it looks at the two groups that are on the horizontal axis, and it says which of those two groups is higher in priority. The nitrogen, which happens to be located on the left. Hence, that structure is known as an L amino acid. If we look at the other form, where is the nitrogen? On the right, we'll refer to that as the D amino acid. Okay? D, again, kind of coming from that dextro that you were suggesting, but dextrorotatory is referring to the light. This is D saying dextro, it's on the right-hand side. It still goes back to the origins of German, okay? Because I think Fischer was German. Okay? So biochemistry is kind of simplified life because we only look at one amino acid type. The other one is not generated. For those of you interested in the philosophy aspect behind biochemistry and where life came from, this is one of those big things that creationists say life can't exist without God. Okay? Because why do we have a preference? If we think back to organic chemistry, there is no preference. When we try and run a reaction that has the potential to produce enantiomers or two products, we get both. Okay? We don't get one and none of the other. Biochemistry produces only one. Okay? So it's kind of an interesting feature. Okay? Why not the R, S, plus, minus, D, or L? Okay. Pessimist, nobody likes to use the same system, and they want to become famous, so they invent a new system. Okay. Optimist, it's slightly different circumstances under which you're working. They're all kind of going back to the same general concept, so it is very possible that these discoveries were made separately, and then somebody brought them all together and said, oh, we're all talking about the same thing, and instead of now everybody agreeing and saying, okay, we're only going to use this system, they all said, screw off, I'm going to use my own system. And they were powerful enough that we end up having to deal with all systems. Yippee. Okay. One more thing to address here. Your textbook kind of uses that dash notation interchangeably. Okay? That dash notation has a very specific meaning. Unfortunately, depending on who you talk to, that meaning means something different. Okay? The way that I use the dash, the smallest point goes out, okay, goes away from that out to the next atom. So the nitrogen is located where if the carbon is in the plane of the paper? In back. Okay? Because our nitrogen is at our point now, where is the carbon located? In back. Are those representing the same structure? No. Okay? The textbook uses them interchangeably. Depending on your references, they may use it interchangeably. Be careful with it. I try to clarify, at least when I draw, you'll never see me change the size. It's always the same length. Okay? It's typically saying going away from your carbon is kind of the reference. Okay? So just kind of be aware of that. Kind of an irritating thing that we got to deal with. So amino acids. We have 20 common ones. Okay? So we've got names associated with them. Okay? And just like we have names, we also have nicknames. Okay? And just like we have nicknames, we decide that's too many letters, and we drop it all the way down to one-letter codes. Okay? Why? Well, the name is long, so I can understand an abbreviation. Okay? Why do we use a three-letter abbreviation instead of a one-letter abbreviation? Well, GLY immediately starts to trigger glycine, because glycine is the only one with GLY. Hey, cool. So that gets me a little bit more information. Why bother to go down to the one-letter code? Remember that ATP synthase molecule? We're looking at hundreds of thousands of proteins or amino acids. Hundreds of thousands of three-letter codes starts to get really big. Okay, so we drop it down to a one-letter code. Okay. All three get used. All three are technically something that you are responsible for in a biochemistry class. Right? And I talked to a student taking biochem at ASU, and that's exactly what they're responsible for. They need to know the one-letter, three-letter, and the name for every single amino acid. Okay? I kind of back off of that because it's not an upper division class. Instead, for the exam, I want you to memorize 5. Okay? Kind of any 5 with one special conditional, which we'll talk about here in just a second. Okay? For the homework, you're just expected to look them up. Okay? If you don't have the textbook, look up table, amino acids, Google. Awesome, it'll list them all for you. Okay? So this is where it gets kind of to the activity. We'll skip task 1, because nobody likes enantiomers, and I don't feel like playing with the model kits right now. And we'll move into task 2. Each of those amino acids has a different structure, hence a different name. Okay? Once we've got those, do we really want 20 different classifications? No, it probably makes sense to group them according to similar chemistries. Okay, well, what defines that similar chemistry? Okay. Science, your textbook author, a group of people that got together and said this is the general class. So what I'm going to have you go through and do, assuming I actually got this right, is you're going to take these flashcards that have the structure, the name, a one-letter code, and a three-letter code on them, and you will work in a couple groups, 2 or 3 groups, 4 groups, at most 5 groups, and you will come up with your own classification system. Okay? So I just want you to take them, organize them, make a classification. Encounter is that my access to the textbook images is relatively limited, kind of because, let's pause that real quickly. So this happened to be a category or categorization that I found online that I like a little bit better. Okay, we've got nonpolar, what's referred to as aliphatic groups. Aliphatic meaning, take a look at the structures, pretty much just carbon-hydrogen chains. Are they all carbon-hydrogen chains? No, methionine messes up with a sulfur in there. Okay, why is it included in the nonpolar? Whereas if we looked at the other place sulfur showed up, in cysteine is dropped in the polar. That also has a sulfur. Why does that methyl group all of a sudden change the characteristics? It's not terminal. Okay? That methyl group is large enough that it hides most of the sulfur's electron density, which makes methionine nonpolar. The hydrogen is so small, okay, that sulfur's chemistry now becomes much more accessible. Okay? Take it a step further. Do you guys remember the difference between SH versus OH as far as acidity goes? Okay. So ignore what they're attached to. Glue on my pen fell apart, so now it's not working right. So attached out, we've got an OH versus an SH. Which one is more acidic? Why the SH? Okay, why is it more willing to give up the hydrogen? So when we're thinking about stability or reactivity of our acids and bases, one of the things we need to think about is stability. So we'll look for charge. Are they both charged? Yes. If we get rid of the hydrogen, both structures are charged. Okay. What's the next thing we should look at? Size. Is there a difference in size between sulfur and oxygen? Sulfur is bigger. By it being larger, that negative charge is now dispersed across a larger area, which means it's more stable. If this species is more stable, what does that mean about the ability to remove the hydrogen? Much easier. SH actually becomes more acidic than an OH. Okay? Even though OH gives us hydrogen bonding, SH really kind of brings in a massive polarity by ditching that hydrogen pretty quickly. Okay? So we can then kind of subdivide things out. You'll notice we have our aromatics. You notice with tryptophan, where'd they place tryptophan? Up in the aromatic section, not according to its polarity with the nitrogen. Again, largely because that polarity is probably not enough to overwhelm the larger ring structure. Our polar uncharged. Okay? Looks like almost everybody had some kind of polar section with no charges associated with it, and when we list them all out, we've got all of those popping up. Is there a weird one in there? Proline. Most people had proline and couldn't quite figure out what to do with proline. Because it looks weird. Why does it look weird? Where's the R group? If we look at all of our other structures, the R group is attached to what? The amine, the carbon, the acid, and most of our amino acids. The carbon. Where's the R group located in proline? The carbon and the amine. It actually loops back on itself. That meant that the nitrogen ended up looking really weird and went from an NH3 to an NH2, and everybody kind of panics about it. Okay? It's still really the same effective reactivity as the NH3. It's just the proline structure folded back on it. Okay? Why does it end up being polar? Well, because the side chain is clearly polar, right, with all those carbons and hydrogens? Okay, no. So why is it polar? What can all of our other amino acids, and particularly those R groups, do? They can, oh, that was a little faster than I thought. They can all freely rotate. Why can they all freely rotate? They are all connected using sigma bonds, or single bonds to the amino acid backbone. Okay? But isn't proline also connected using a sigma bond? But it's enclosed back in a ring, which then means, can I rotate? No. Which then means the polarity of our acid and our amine on the other end can't get neutral out by free rotation. Those will always get locked into that relative location, and it ends up becoming a little bit more polar because of it. Okay? Is it that polar? Maybe. It again depends on the classification. Proline can jump back and forth between nonpolar and polar depending on what you want to look at. Okay, so Jen, and then maybe Mike.
I was just going to ask because the book has it as proline and nonpolar.
And proline very typically can be slid up into the nonpolar for that very reason. So it's what level are we looking at? How does it affect the overall structure? Okay, and proline becomes an incredibly useful amino acid when we're looking at larger, when we actually go out to protein structure as opposed to amino acid structure. Okay? It actually dictates a lot of really important structural effects because of this locked ring position. Do you have a question too? Okay. The part that I prefer about this list is they refer to these as positively charged R groups and negatively charged R groups. Okay? Did you guys use that, or did you pick a different term? Everybody used positively and negatively? Didn't use any other terms? Like acid or base? Okay. I would argue that's a good thing. Your textbook labels them as acids and bases. The negatively charged R groups, they label as acids. Okay. Why might I kind of freak out at that? If I look at an example acid, okay, give me an acid, any acid you want. HCl. When HCl acts as an acid, what does it make? H plus, which is the acid part, so let's ignore that, and Cl minus. When we said an example acid, did you tell me chloride? No, you told me HCl. When we look at the acid functional groups, do you have an acidic hydrogen? No. Aspartate and glutamate are the equivalent of chloride. Chloride's not an acid. If we put the hydrogen on, it becomes acidic. Why are they getting called acid functional groups? If we ignore biological pH, and just take it into a standard system and filled out and made sure that everything was neutral, we have COOH, which is known as carboxylic acid. That's why they're naming it that. Why is that exceptionally misleading? When you take that and put it into biological pH, it loses that hydrogen very quickly, and it's not acidic, it's negatively charged. Okay? So we have to be a little bit careful with those terms, acids and bases, because they imply a lot of chemistry behind them that isn't necessarily true. Conversely, if we look at the positively charged R groups, NH3 plus, okay, similar to, how about NH4 plus? How would I expect NH4 plus to react? As a hint, acid or base? Okay, to act as a base, what has to happen? It must share electrons with a hydrogen to become NH5 double plus. Can nitrogen have 5 bonds? Does NH4 act as a base?
No.
What does it act as?
Acid.
An acid. And yet, every place that I see the equivalent of NH4, NH3 plus, NH2 plus, one of those is positive, though we can't quite see it. What are we classifying it as according to the book? A base. Okay. Because when we go back to our organic mindset and ignore the pH at which we're at, the nitrogen would act as a base. But at physiological pH, it doesn't. Okay? So we have to be very careful that we're stepping out of organic chemistry and saying, I dictate the conditions so the structure is what I say it is, to now biochemistry, where I don't dictate the conditions. Those conditions are dictated for me. I put my compounds into it. Those compounds must react with those conditions, and then I can evaluate it. Okay? So categories that remove the chemistry understanding are probably more relevant: negative, positive, aromatic, nonpolar, polar. Because once you have that structure at physiological pH, you can then say, well, what happens if I add an acid? Okay. If we labeled it as an acidic functional group and I added an acid, what would you say happened? Acid and acid, nothing should happen. And yet what does happen? It picks up a hydrogen. Okay, so we have to be careful with looking at those structures and interpreting them according to the environment that we're in. Okay. Tricky. Watch out for it. Questions? Okay. pKa of the carboxylic acid.
2.
pKa of a nitrogen. Okay. Which we said was misleading. Okay. But here we're getting into that acid-base character. So we look at this, we've got a generic amino acid. Is this a valid structure? I know that sounded like I was going to say something else, but let's just pretend I wasn't going to. Is that a valid structure? Is that a valid structure for biochemistry? No. Why not? What's that?
Because it doesn't show you whether the amino is a D or N.
Okay, let's fix that. So you can't say that. Okay, so there's usually charges. Okay, we're usually at physiological pH. And at physiological pH, we'd be at a pH of 7. So what would happen to the structure if I was at physiological pH?
Deprotonate.
It would deprotonate. Deprotonates everything? So the structure should be this guy. And H. And a minus, and then an O minus.
Keep the O, change the N.
Okay, keep the O, change the N. So you said it should be deprotonated. So is that the deprotonated state for the nitrogen?
Mm-hmm.
That is the deprotonated state for our nitrogen, yes, unfortunately. But you said it should be deprotonated at physiological pH. Ray, do you disagree with that?
Should be pro-
It should be protonated. Well, son of a... Why is it protonated?
Because the physiological pH is less than, or more acidic than the pH.
When deciding the charge state, it's not the pH to the molecule, it's the pH to each functional group. So when I'm deciding the charge state for that oxygen, I'm comparing the pH to the pKa. The pKa is 2, the pH is 7-ish. Okay? That means that conditions I'm in are more basic than my functional group. If they are more basic, should I have put the hydrogen on or take the hydrogen off? I'm in a more basic environment. Take it off, which is why I'd be at the minus charge. Okay. I can't apply that to the whole molecule because the whole molecule doesn't carry a pKa of 2. Only the carboxylic acid carries the pKa of 2. The amine carries a pKa of 9. I now have to compare that back to my pH. My pH is 7. Okay. Am I more acidic or more basic than my functional group? I'm more acidic, which means I have to put the proton on, and I go to NH3+. Okay? The molecule at this condition is still overall neutral, but I've got the appropriate structural features behind this now. Okay? So we have to apply that. Remember when we talked about pH back to pKa? It's popped up a couple times. It's popping up again with our amino acids. We have to be able to apply that back to our structure. Okay, which means we need to know the pKa of the amine and of the acid. That's why I told you to memorize it. What is today? Thursday? Tuesday, right? Okay, so you need to know those. What happens if we change the amino acid to an R group that could potentially have a pKa?
That might be protonated or deprotonated.
That now also must be evaluated, and I have to decide if it's protonated or deprotonated. Okay. Is it important to look at this? Well, our charge is going to change how the amino acid reacts with water or interacts with water. Yes. So is understanding something about how it reacts or interacts with water going to be important? 80% of our cells are water. That's pretty darn important. So we have to be able to specify those changes in charge and how they contribute. Okay? So if we move to really, really low pH, you didn't see that. Low pH. pH of 1. What happens to the structure? Careful, I don't know what dissociates means. I'm at a pH of 1. Should that structure change or should it stay the same? Should change. How should it change? We're comparing the pH to the pKa. The pH is 2. What is the pKa of the carboxylic acid? 2. So the pH is more acidic than my pKa, which means should I be in the protonated state or the deprotonated state? Protonated. Is my structure of the carboxylic acid shown in the protonated state? Protonated, yes. Okay. The deprotonated state is O-. Okay. So that's fine. What about the NH3? NH2. Okay. The amines pKa is 9. I'm at a pH of 1. I'm more acidic than my pKa, which means I must be in the protonated state. What is the protonated state for the amine? That is the NH3. Okay. And conversely, if we now flipped this on its head and went to an exceptionally basic environment or a very high pH, now what happens? Both positions need to become deprotonated. What is the deprotonated state for the amine? NH2. What is the deprotonated state for the carboxylic acid? O-. Okay? Anywhere in between was the structure that we evaluated where the nitrogen was positive and the oxygen was negative. Right? Which, because I've got them up there, might as well. NH3 plus, COO minus, R, whoops, plus. Right? Right? What is the charge on the molecule at low pH? We look at this one, it's positive, right? What is the charge on the molecule at high pH? Negative. What is the charge somewhere in the middle? Neutral. Okay. What are all things striving for? Neutrality. So when we're thinking about our amino acids, one of the things that we're going to be primarily concerned about is when do they become neutral? Okay. What pH do they become neutral? That gets referred to as the PI, okay, which is quite likely going to get talked about today. Let's evaluate this positive and negative thing, because that can help us out. Define an acid. Proton donor. What's the charge on a proton? Positive. So when we're at low pH, what do we expect our charge to be? Positive, because there's lots of protons. Okay. We defined a base, that's proton acceptor, that doesn't really help us out. So let's run with a base example. Example base. NaOH, sodium hydroxide. Sodium is always a spectator ion. Get rid of it. We have hydroxide. The charge on hydroxide? Negative. What should our charge be expected to be at high pH? Negative. It matches. Okay. So we can come up with some rough approximations to help us kind of nail down those charges and at least get us in the right frame of mind. Kind of make sense? Okay. That in-between state is known as the Witter ion. I almost always forget to mention that. Thank you for mentioning it earlier. Okay. What does Witter mean? German speakers? Usually you get like one. Okay. Maybe? No? Is that not true? Okay. It's too small a class. Witter means twin, and since there's no German speakers, I can just say that. It means twin. Okay, twin ions. So what are we saying? We have a positive and negative charge. Those are the twin ion states. Okay? So that middle structure that has now been deleted, okay, was both positive and negative. We have the Witter ion. Okay? So since everybody loved the titration curve, let's go back to it. Okay? But now we're not looking at a generic acid. We'll pick a specific structure. We will pick tyrosine. Take a look at this structure, okay, for tyrosine. What do you think? Are we at low pH, high pH, physiological pH? That's a horrible statement to make, but we're going to do it anyway. What do you think? If it was at low pH, what would we expect our charge to be? Positive, just like hydrogen. Okay? If it was at high pH, we'd expect negative. Okay? What is the charge? Neutral, so we're probably sitting somewhere in the physiological range, somewhere in between those. Okay? Which was a bit misleading because this came from me copying and pasting and not fixing it appropriately. When we're starting a titration curve, we very typically start at the low pH and we titrate in base. Okay? That is not the appropriate structure to start with if we're starting at low pH. If we're at low pH, what should our structure look like? We should have the carboxylic acid be protonated. Okay. What about the amine? The amine has a pKa of 9. If I'm at a lower pH, I'm more acidic than my pKa. It needs to be protonated. It is drawn protonated, so that's okay. Make sense? What happens as I slowly add base? The most acidic functional group reacts. Okay? It will react according to its Ka. Yeah, that comes back too. Okay. Kas are difficult, so we typically represent them as our pKas. That's why we talked about 9 and 2. Okay, so when we look at this structure, where do we have acidic functionalities? Carboxylic acid, that's a very good start. The amine has an acidic hydrogen. Come on, organic chemists. That is a phenol, and phenols are acidic. So we have 3 acid sites within this molecule. As I add base, I'm going to slowly remove the most acidic hydrogen until that hydrogen is all gone. Effectively a buffer. Okay? Which of those 3 functional groups is the most acidic? Carboxylic acid is called an acid for a reason. Okay? It's the most acidic. Okay? And I'm actually going to look like an idiot here in just a second. Whoa! That was a bit excessive. So we slowly add, and we end up seeing, oh yeah, and that was a hydrogen. We slowly start seeing our structure change. Okay? All the way through. With plus, this was still our OH. We add more base, we react. The next hydrogen, the structure changes again. Until eventually we end up with this whole thing, which I was going to stepwise, but so much for that. Okay? And we'd have each of the pKa's for each of those steps labeled out. Okay? Does anybody know the pKa without this slide of the phenol functional group? Okay. Theoretically, in organic chemistry, you were told to memorize it. Okay. Nobody does. It's okay. It comes in about a pKa of 10. Okay, so it is actually the least acidic of all of those. And so we see that hydrogen disappear at the very tail end of this. Okay. We could go through and evaluate and determine the pKa's for each of those functionalities off of a titration curve by looking at our ideal buffer point. And we should have 3 buffer points. Okay. The next thing that we want to kind of address here would be the charge. I think I want to address the charge. What is our overall charge at the beginning? The next state? Oh, that's why. Remember the beginning had that typo. I was like, something's really wrong here. I can't figure it out. Remember I had that typo? What's the charge at the beginning? Positive. The next one? The next one? Next one? 2 negative. Okay, we said one of the most important things to evaluate would be our neutral state. Okay. Would I be able to look at a titration curve and determine when I have just this structure? Yes. Remember, as we transition, we go from HA to A minus. We're starting at effectively HA going to A minus. When are we all HA? The very beginning. When are we all A minus? As soon as we hit that equivalence point. So yeah, I can determine the exact point that that happens off of a titration curve. Can I do it with this data? That one gets trickier. Maybe it helps if we look at an actual titration curve. So if we were going to predict our titration curve for tyrosine, it's going to look pretty awful. That's 2. Okay, it spiked. This was 9. Don't trust scale. That was, yeah, really don't trust scale. 10. And then it spikes again because we're all out. Okay. We start at the very, very bottom. We're starting here with what? H, how many acidic hydrogens? 3. A going to 2A going to oh, that was neutral, sorry, because this one was positive. So I start at the very beginning at H3A plus, which then goes to H2A, which happens at the equivalence point for that one. Okay. Which then goes up at our next spike to HA minus, which then goes up at our next spike to A minus 2. I want to know, that point. Well, off the titration curve, where is that point? I can say the pH, assuming we had this to scale, okay, would be pretty cleanly, easily obvious. I just read it right off the curve. But what if I didn't have the titration curve? Where is that point relative to some other points that I can nail down? It is halfway between half equivalence number 2 and half equivalence number 1. Do I know the half equivalence number 1 and the half equivalence number 2? What are those numerical values? It's the pKa for that acid. So I can look at just the pKa's and I can determine when I'm going to have my neutral structure by taking the halfway point between those two pKa's. Do I need to use the third pKa? No. All I care about is the 0 point, when it's zeroed. That's just those 2 points. It's halfway between those two. Okay? I could bring in the third one, and then it would probably be something like a third of the way, and you really don't want to do that. Okay? So we're looking at that half position. That gets us our point, or our pH, when our structure is entirely neutral. Okay? If we compared all of the structures when they're all entirely neutral, they would all be the same electronic charge. Same electronic charge is more fancily known as, it's a bit of a leap, but we got it, maybe. What? No. Begins with an I. Isoelectric. The point at, or the pH at which my amino acid has no charge, or no overall charge, is known as the isoelectric point. Okay. Because we're reading it off the pH scale, we refer to it as the PI. Your textbook does not use a titration curve to look at this. It uses the pKa's in some fashion that makes absolutely no freaking sense to me. You are taking the average of your pKa's around the isoelectric point. So for glycine, alanine, valine, leucine, all the way up to proline, there's only 2 pKa's, which means the PI is just the average of those 2 values. How do we determine the PI for all the other ones? I have to make sure I average the correct 2 pKa's. If I pick the 2 wrong ones, I get the wrong answer. So I have to be able to center that appropriately around it. Okay? Your textbook, again, lists some way of determining that makes no sense to me, and I've never consistently been able to use it, and because of that, I won't use it. The way that I do it is looking at the structures. Okay? Which, yes, means you have to draw out the structures, but it gets you to the answer correctly every single time. It allows you to use the proper 2 pKa's. Okay? So when we look at this, remember that was an H. Okay? We're looking for the point at which my structure is neutral. That's this one. I average the pKa's around that point. So I average pKa1 with pKa2 for the case of tyrosine. If I move to a different amino acid, I may be averaging pKa2 with pKa3. Okay? It's all going to come down to that amino acid and its charge state within the structure. Okay? If by any means you can come up with what the textbook is trying to say and consistently find the PI, please let me know. I would love to know how that works. Okay? The other option, and you'll love this one, how else do we figure out the PI? You memorize it. I have a feeling you don't want to do that. Okay? So pKa's that you should know for the acid, because the acid is 2. We take a look at the acid functionality. All of those pKa's are ballpark 2. The amine you should have memorized because they're all ballpark 9. Okay? So for all amino acids, those are true. The ones that become tricky are, what is that, 7? 1, 2, 3, 4, 5, 6, 7. The last 7 in this chart. Okay? Those 7 are then also going to dictate the PI's. Because if you go through and look at your PIs will almost all sit at PI. It's the average of 2 and 9, which sits about 5. Okay? And sorry, I talked too long. I got to stop there.